Assalamualaikum, very good day to everyone. My name is Elyasa and my number is 19845. Today I will present the static EMM3103 from chapter 1 till chapter 4. So the context of my presentation basically the first one is the basic concept of static. Second one is force system, and then equilibrium, and then I will go through analysis of frictions in bodies and structures under static conditions. So the first one is the basic concept in static. Basically, a static is a branch of mechanics which deals with the study of the conditions under which rigid bodies are at rest. So basically, a static is a great importance because the device that engineers need to remain static in equilibrium. So these are the basic concepts which units that we use in static. We have the length, time, mass, and force. In either we use SI unit and or US unit. So the idealization basically we have three rigid particle, rigid body, and rigid force. So particle has a mass, but its size can be rejected. The C is a principle of magnets reduced to a radius simplified form. With the geometry of the body will not be involved in the analysis of the problem. And the rigid body is basically a combination of a large number of particles which remains at a fixed distance from one another. And the concentrated force basically the effect of a loading which is assumed to act at a point on the body. Basically, load can be represented by a concentrated force. So these are the Newton's law of motion will be used in the static. The first law is basically is the resultant force acting on the particle is zero. Particle will remain at rest or will move with a constant speed in a straight line. As you can see from this, all the forces will combine and will make it the rigid body to become at rest, or it will move at a constant velocity. And the second law is basically if the resultant force acting on the particle is not zero, the particle will have an acceleration which is proportional to the magnitude of the resultant force, which is the F and E. These are the equations for the force. And the third law states that the force of the action and reaction between bodies in contact have the same magnitude, the same line of action but opposite signs. These are the diagrams for the third law. So we move on to the force system. For system, the Q can be defined as the cause of change in the state of motion for a particle or body. It is a product of a mass of particle and its acceleration, which is force is equal to mass times acceleration. And the force has a characteristic. It is a magnitude. That it has a magnitude, direction, points of application, and line of action. Later on, I will show you. And force is represented as a vector because it has a magnitude and direction. So these are the examples of vector force. Which is it has the magnitude for the force and has the direction. It has the point of two, and also it has a line of action. And for force factor, it has a scalar. The scalar is any positive or negative physical quantity that can be completely specified by its individual example. Its length, mass, and time. As for a vector, it's a physical quantity that requires both of the magnitude and the direction. For example, like force, positions, and moment. What is force system? Force system is basically a combination of many force acting on the same object. So the force system have a coplanar and non-coplanar. So these are the names for the branch under it. So these are the figures for each of the types for coplanar and non-coplanar. So vector operations, we have three basically. The first one is the vector addition. Vector addition is the addition of two vectors A and B with a resultant vector R by a parallelogram law. So it resulted as R is equal to A plus B or B plus C. So if you can see from here, this addition of collinear vectors, you can see from here, And the parallelogram will be static and triangle constitutions and for the second one is a vector subtraction. Actually, it's the same as a vector addition. However, it is one of the um, line has the opposite direction, so it will be subtract. So the last one is the dot product. A dot product is a two between two vectors A and B yield a scalar. So the dot product can be used to determine the angle between A and B. As you can see from here, using dot product to determine the angle between B. And the dot product is also used to determine the projected component of a vector A onto the axis EE defined by its unit vector. As you can see from this, and these are the equations used for the dot product. So for vector representative, basically force can be represented by two standards, which is polar notation form and Cartesian form. So these are the standards for the polar notations and these are for the Cartesian. And the parallelogram law, which is a way to determine the resulting force for the two dimensions. So we use a parallelogram law. So two forces added according to the parallelogram law, which is it has a component of force, as you can see from here, and we can find the component of resultant by using equations of law of cosinus and law of sinus, as you can as stated here. And we need to construct a diagram to make it a triangle so that we can find the angle for the components of resultant. And then the second method to find the resultant force is the rectangular component for two dimensions. So a vector fx and fy are rectangular component of f, and the resultant force is determined from the algebraic sum of its components. As you can see from this diagram, these are how we determine which we separate the x-axis and y-axis, and then we combine it. So we can find the resultant by these equations and also the angle by these equations. This is an example for two dimensions, which we using this diagram. The linear and the figure is subjected to two force F1 and F2. So determine the magnitude of directions of the resultant force. Specifically using the second one, using the rectangle. First one, we just separate the force by their axis. It is the x-axis and the y-axis. For F1, we separated 650, which is the angle is 50, and 400 sine 45, because it has the angle of 45, and then we want to find the x-axis. And then for same as the y-axis, 600 sine 50 and 400 cos 45. And then we get each of the force for axis, and then we find the resultant force by using this equation, and we find the angle, and we write the answer in this form, which is the polar notation form. And then this conversion in Cartesian form, basically using each of the force in different in one force it has two different axes. It is the 600 cos 50 is for x-axis and 600 sin 50 is for y-axis. It is the same for force 2, and then we combine it together, sum it together, and then these are the answers. As you can see from here, this can be the same answer as the first one just now. So these are the Cartesian vectors. For three dimensions, we want to find the resultant force for the three dimensions. So using this equation, it is the magnitude of Cartesian vector and coordinate by direction angle. So these are the examples of 3D. So two forces act on the cube shown in figure. Specify the magnitude of F2 and its coordinate direction angle so that the resultant force Fr acts along the positive y axis and has a magnitude of 800, which means that already giving us the resultant force, which is 800 at the y-axis. However, we want to find the magnitude of F2. So these are the answer. Okay, firstly, we find using the Cartesian form, which for force one, we separate for three axes, which is x, y, and z. 300 cos 45, 300 cos 60, and 301 cos 120 for force one. We divide it for like its own axis, and then we make it like this. And for force two, we don't know yet, so we already know the resultant force, so we can make it the resultant force equal to force one plus force two, so we can know what is each of the axes for force two. As you can see from here, it's already separated for each of the axes. So 800 joule is for y-axis, so only y-axis has the numbers here, and the other two x-axis and z-axis have 0. So we can find the values here, and then we find the resultant force and find the angle using the previous equation. So this is the answer. So y is here, and E alpha is here, and beta is here. So we proceed with the next, which is equilibrium. What is equilibrium? Equilibrium particle is said to be equilibrium if it remains at rest, if it is originally at rest, or has a constant velocity if originally in motion. So to maintain equilibrium, it is necessary to satisfy Newton's first law of motion, which requires the resultant force acting on the particle to be equal to 0. So these are the equations where the sum of force is the vector sum of all the forces acting on the particle will be equal to 0. And then the free body diagram. The free body diagram is basically a drawing that shows the particle with all the forces that act on it, and it's called a free body diagram. So the procedure how to draw it, basically we draw the outline shape. These are the examples on how we want to draw free body diagram from this. So firstly we draw the outline shape. So the outline shape is the first, and then show all the forces. So all the forces from this spring A and B, and also the weight of the point, the plate, sorry. So the plate, and then identify each forces. So we identify this with string A, CA. So string B, CB, and the weight we already know the weight of it, so the value. So we just put the value. So we proceed with the equilibrium of particle. Basically, we have two-dimensionals and three-dimensionals. For equilibrium, all the forces, the sum of the forces is equal to 0. For three-dimensional, include the x-axis. So these are the examples for 2D. So determine the tension in cables CT and DC necessary to support the 60 kg cylinder in figure. As you can see, these are the figures. We already have the weight of the D, and we have the angle here, A and B, and we want to know the resultant force of DC and DC. So these are the free body diagram. For the weight, we already know, so 60 times the gravitational force is 9.81, and then it will equal to the tension the outside, because it didn't move, so it will be the same. And then these are the full body diagram, which we already have the changes for B at TBB, and we want to know the DC and the TBC and TBC. So how we want to calculate it? Basically, it's the same. We separate it by the axis. So firstly, we want to know the x-axis. So TC cos 45 minus the 4/5. Basically, we want to know the at adjacent because we want to use the cos. So cos so adjacent divided by the hypotenuse times with the cos, it will become a negative because it's the opposite direction of the x equal to 0 because it's equilibrium. Same as the fy here, but it includes the weight because we already know the weight, so it will be negative because it's the opposite direction. And then from that we can know the PC here and PA if we substitute it using a simultaneous equation. So these are the examples for 3D. Basically, we already know the weight, which is nicely load, and it's dependent from the full social integer. The gender is supported by two cables and string having a spacing T500, assuming the force in the cable, the stress of the string for the equilibrium, and cable AB, light in XY plane, and cable EC light in the x plane. So these are the body diagrams. So first we separate it by the force by axis. So we calculate the x-axis first. For the FB, we can know the x-axis by FT sine 50, and for FT, we can know it by 4/5 ft equal to 0, and Fy, we already know by the same method, and LZ also, but we include the 90 which is the weight of the load, and then we can know the FB, and we can also know the FB, the spring, the stress of the spring, because they have the spring in the FB, so we can know the stress of the spring as using this equation. So the equilibrium for the rigid body. So just now we using the equilibrium of the particle. Now we proceed with the rigid body. So it also has a 2-dimension and 3-dimension. However, it includes the moment. So moment is equal to 0, which means the moment is the force times the length, and all of these are the same. And then for example, for 2D, for the rigid body, basically determine the horizontal and vertical component of reaction on the beam caused by the pin at B and the rocket at A, as shown in figure, we get the weight of the beam. So we have this force, and this force. We also have the normal force. So these are the body diagrams that we can create. So these are the normal force, and these are the force acting upon this rigid body. And firstly, we separate it by activities, the force, and then 600 cos 45 minus x, which is this force to the 0, and dx we know the value. And then we go to the moment. Moment for this force will be 100 times 2, which is the length between dy and d, and plus 600 times 45, which is the force, times 5, which is the length also, which is 2 times 3, and then minus 600 cos 45 times 0 2, and minus ay. Ay is the force that we don't know, is equal to 0. So we can know the value for ay, and summoning the force in the y direction using this result is the result for dy. This is the same method. However, we can find the different value. So these are for the example of 3 dimensions. So these are the question figure. So the homogeneous state shown in figure 5 has a mass of 100 grams. So the 100 grams is the weight, and is subjected to a force and a couple moments along its edges. It is supported in the horizontal plane by a rod at E, a bolt and a basket joint at B, and a cord at C, determine the components of reactions at C support. Actually, just like I mentioned just now, we divide it by its axis. For Fx, we don't have it, and Fy, we also don't have it. And Fz, we have the AZ, Z, and PC, and 300, and 981. And then is a 0, and moment is we have this one equation, and x and y is stated like this. And then using a simultaneous, we can find this value. So the last topic for today is the analysis of friction in the bodies and the structures under static conditions. So what is friction? Friction is the force that resists the movement of two convective substances that slide relative to one another. This force always acts tangent to the surface of the point of contact and is directly to oppose the possible r-axis motion between the surfaces. So basically in the topic we will be discussing on the dry friction. It is sometimes called column friction, occur between the contacting surfaces or bodies when there is no lubricating fluid. So these are the equations. Basically, the difference between a nu S and nu T is nu S is for static friction, where they have no motion of the rigid body. However, for the kinetic frictions, the rigid body is non-moving. So these are the characteristics of dry friction. And types of friction problems, basically have three. The first one is no apparent impending motion. Problems in this category are strictly equilibrium problems, which require the numbers of unknowns to be equal to the numbers of available equilibrium equations. So as you can see from this figure, the numerical value must be checked to be sure they satisfy the inequality F equal to mu S n. Otherwise, the splitting will occur. So the second one is impending motion at all points of contact. In this case, the total number of unknown will equal to the total number of available equilibrium equations plus the total number of available friction equations. So this are in the picture. And then the last one is impending motion at some point of contact. Here the number of unknown will be less than the number of available equilibrium equations plus the number of available frictional equations or conditional equations for friction. As a result, several possibilities for motions or impending motion will exist. And then these are the examples. Basically, a uniform 10 kilograms ladder in the figure rests against a smooth wall at B and the end of A rests on the rough horizontal plane, for which the coefficient of static friction is mu as 0.3. Determine the angle of inclination of the ladder and the normal reaction at C if the ladder is on the verge of splitting. So if the ladder is on the verge of splitting, so the mu will be 0.3. Using the mu as into, and then we separate by x-axis and y-axis also. So we're using the y-axis, we have the normal minus with the weight of the stair times with the gravitational force is equal to 0, and we can find the normal force. And from it, we can know the force for B direction. And then we can also find the moment, and from there we can know the angles of the stair. With that, thank you.